All right, so today we'll be working with rules of differentiation, which are going to be the quotient rule and the product rule. So let's start off with the product rule first. So when you're talking about the product rule of differentiation, you may recall that when you're talking about the d by dx is a linear operator, right? So we're just using it for linear expressions. In product rules of differentiation, you have two expressions that are being multiplied with each other. So if you have f of x multiplied with g of x, you're going to be applying the product rule over here. And the product rule basically states that you take the first expression multiplied with the differential of the second expression. This is going to give you first term plus. Now you take the second expression and multiply it with the differential of the first expression. And that is how you're going to differentiate an expression that has a product of two functions. So we're going to look into how we can do this. If you have, this is basically the formula for it. If you have a question that says that you have to find the derivative of the product of the functions f of x is equal to 2x and g of x is equal to sine of x. So your f of x is 2x and g of x is sine x. The derivative of sine x is given, which is cos x. So if I'm multiplying them, and I have to find the derivative of this multiple, so d upon dx is going to give me f of x into the differential of gx, g dash x, plus g of x into the differential of f of x. So now what we're going to do is we're going to substitute all of these into the equation and see what we're getting. So f of x comes as it is, so 2 times of x multiplied with the differential of gx which is basically cos of x, plus g of x, which is basically sine x, into f dash of x. So differential of f of x comes out to be 2. And then you can write it as a linear expression. So 2x cos x plus 2 sine of x, which is going to be your final answer for the differential of f of x into g of x. So this is how you're going to apply the product rule to the multiplication of two functions and to basically differentiate them, right? Now, in the same way, there's the quotient rule of differentiation. The quotient rule of differentiation states that when you have two functions that are being divided with each other, that is when you apply this rule. And the formula to apply this rule is you take the lower function first, multiplied with the differential of the upper function. Now, instead of adding it, we're going to subtract it. Subtract the upper function into the differential of the lower function. And there's an extra step over here where you have to take the denominator square. So whatever is your lower function goes into the square. So this is the basic formula that you're going to be applying. This is given over here. Now we'll look into how we apply this formula into different questions. So now you have to find the derivative of the quotient fx over gx as well as gx over fx for f of x is equal to 2x and g of x is equal to sine x. So let's do it for both of them. First, we're going to apply it for fx over gx. So f of x over g of x and this is the differential of with x, right? So what we're going to do is, first we're going to take the lower function, that is g of x. Let's just write the function here. So g of x is sine x multiplied with the differential of the upper function, 2x differential 2 minus, now you write the upper function first, so 2x into the differential of the second function, that is sine x. So the differential is cos of x divided by the lower function square. So sine x is squared. You can simplify it, write it as 2 sine x minus 2x cos of x divided by sine square x. This is going to be the differential for f of x over g of x. Now let's try the same thing for g of x over f of x. So if I'm finding the differential of g of x over f of x with respect to dx, now my lower function is f of x, so 2x into the differential of the upper function that comes out to be 2x, sorry, cos x, minus, now I'm going to write the lower function first, so sine of x into the differential of the upper function that comes out to be 2, divided by the lower function square, which in this case is going to be 2x squared. So this comes out to be 2x cos x minus 2 sin x divided by 4x squared. You can also take the common out, so you have 2 common. It gives you x cos x minus sin x divided by 4x squared. Cancel 2 and 4. You're going to be left with x cos x minus sin x divided by 2. And that's going to be your final answer for it. So basically, this is all you need to know regarding the quotient and the product rules. We're now going to practice a few questions for your past papers to see the kind of questions that you can expect in your exam. So if you have a question like this and they ask you to differentiate it, you have to differentiate both of these expressions, right? This is going to be our first expression, and this is going to be our second expression. So to do this, you have two options. Either you multiply this throughout and you make a linear expression and then differentiate it through simple differentiation. However, what we're going to do here is we're going to apply the product rule. Now we're going to do, what we're going to do is we're going to take this as our first function, this as our second function. So if I'm differentiating f dash t, I'm applying the product rule over here. So the first function comes as it is. I have 4t square minus t. I multiplied with the differential of the second function. So I'm going to differentiate each of the terms. T cube gives me 3t square minus 8t square gives me minus 16t and 12 becomes 0. Plus, now I'm going to write the second function first. So t cube minus 8t square plus 12, which gets multiplied with the differential of the first function that comes out to be 8t minus 1. Now I can expand it. I'm going to multiply 4t squared, this entire bracket with the other bracket. So I have 12t cube minus 64t cube. All right, so this is 3t squared. I forgot this here. That's going to make my first term 12t5. Yeah, minus 12t4. So 12t4 minus 64t cube. Now I have to multiply minus t. So I have minus 3t cube plus 16t square. Likewise, I'm going to now multiply this bracket. So I have plus 8t raised to the power of 4 minus t cube minus 64t cube plus 8t square plus, 12 into 8. So 12 into 8 gives me 6 and 96 t minus 12. Now I'm going to expand it. So simplify it through all of these terms. So I have 12t4 and 16, I have 12t4 and 8t4, which is going to give me 20t4. So 20t4. Now in cubic terms, I have 64, I have minus 3, I have minus 1, and I have minus 64. So minus 64 and minus 64 is going to give me 128t cube. And minus 3 and minus 1 is going to give me minus 4t. Now the square terms, so 16 and 8, 16 plus 8 gives me 24t square plus 96t minus 12. You can also expand these two, so simplify them. 20t raised to the power of 4 minus 132t cube plus 24t square plus 96t minus 12. That is going to be your final answer. Now it's up to you if you apply the product rule here or you multiply the brackets, expand them, and convert it into a linear expression to apply basic differentiation to it. Likewise, here's another question where the expressions are being divided now, right? So what we're going to do in this case is we're going to apply the quotient rule here. So this is my lower expression and this is my upper expression. So let's try the quotient rule now. So g dash of x, I have the lower function 2 minus x multiplied with the differential of the upper function that gives me 12x minus the upper expression that is 6x squared multiplied with the differential of the lower expression that is just minus 1 divided by the lower expression square. So 2x minus square. Now this gives me 24x minus 12x squared plus 6x squared divided by 2 minus x whole square. That's going to give you 24x minus 12x squared plus 6x squared gives you minus 6x squared divided by, you can just leave it as 2 minus x whole square. And that's going to be your final answer for the quotient. I'm sure you guys are familiar with both the rules now. This is going to be all for this lecture now.